this is our misfit function. Okay, so if you can tell, this is the L2 norm. You have this observed data we call the yi. It's the label, you do it manually. And then this guy is our forward propagation algorithm. So also we can call it the predicted data. So yi minus predicted data and take the L2 norm. So now we want to find a recursive way to compute partial derivatives. So in order to solve this problem, we need to use the chain rule because we have a set of algorithms. So let's decompose this algorithm layer by layer. So first, we take out the most outside part. So the third layer. So the partial sigma 3 and partial W3 equals partial sigma 3, partial Z3, and partial Z3, partial W3. This is a very typical chain rule. So I assume you guys know chain rules, right? Everyone knows? Okay, that's good. And here we put notation that this is quite natural, that you have a function, it's a function of zi, and so the derivative should be this guy. And also here zi, the notation of zi is the weighted function, weighted sum. So we use is a representation of this guy. And the dzi over dwi is sigma I in the minus 1. This is easy. This can be derived from this guy, right? So zi, you take a derivative of wi, then you get this guy, right? Okay. And the last one, dzi over d sigma I is wi. Also use this equation. You can see and straightforwardly get this guy. So let's remember all of these, and which we use it in our derivation. So first, we use a chain rule to decompose the third layer, and then use the third layer. We go back to the second layer. So instead of, you can see here, it's still the same as the previous layer, but the difference is here. We'll go use the parameters from the second layer to extend the derivation. So you put sigma 2 here, and sigma and z2 here, and then partial w2. So now we get a derivative, respect to the weights in the second layer, right? And then we use this result, we go further back to the first layer. You can see that we do more here, sigma 1, z1, and finally we have derivative respect to w1. And then so on, we can take more, even if you have more layers, w0 or w minus 1, whatever, you can go as many as you want. Okay. And then here comes the question. So we have a long formula, so many terms. How can we calculate these guys? So let's using the result here, and we will substitute these guys back to here, and then calculate the result. So first, right? So this guy, we use the first formula. We get this guy, right? And then let's replace all of the sigma 3 pieces. And then this guy, partial z3, partial sigma 2, we can use this equation. Okay, I equals 3, and here should be W2. So we, W3 will replace W3. Okay, and then let's look at this guy. So we still use this equation. Now it's become d sigma 2, right? And then same thing, we do say all the same. Okay, so no problem so far? It's clear, right? Everybody follows. Okay. And then we show you a simple MATLAB code. I think it's to make sure you understand. So A3 equals to d sigma 3 times W3. So it's like we'll calculate the first, the third layer, and then we calculate the gradient, right? Gradient this guy, right? D sigma 3, sigma 2, and then we do the loops. Do loops for each layer. So now k equals 2 means we are working on the second layer. So you put your A2 equals A3 here, right? We put the A3 here, getting, and then times W2 and d sigma 2. So, and then we also use the gradient from the previous layer. We put it here, and then we use the formula here to calculate the second layer. And then once you get the second layer gradient, you do the same thing in loop. You get the first layer, and you get the zero layer, and so on. So it's a kind of a recursive way to calculate the gradient associated to your input, which is the first layer, right? Okay, then we use a steepest descent to calculate this unlayered network. So when first let's look at the simple case when n equals to 1. So given x the y, x is input, y is the predicted data. So find the y predict so that the w can minimize the L2 norm. Because now we're only work on one layer, so here is A1 is our output. Okay, so A1 is this formula. I think you've already, if you can recall what we talked about the Ford propagation, we did the sum and with the activation function. And T is observed data, which is the label. One layer. Okay, so you have input features. Use it to calculate A1. Use it as the predicted data. And then let's calculate the gradient. So gradient is, as we said, it's partial epsilon, partial W. So in this case, we have only one layer, so you only have these three terms. And let's look at this guy. The first guy, because it's L2 norm, so this guy should be A1 minus Y, right? Use this guy. It's clear. And then A1, what is A1? A1 is GZ1, right? So this guy should be like this. and then Z1 over WI. And what is Z1? What is Z1? Z1 is the weighted sum, right? So it's Z1 is this guy. So its derivative to the weights should be X, right? Or X here is our input, A0, right? And the second part, GZ, partial G over partial Z, it should be BGZ, right? So this here we don't use. So this depends on what activation you use. So this G here we use the sigmoid, so you can calculate partial G over partial Z here, put it here, right? Okay, so you can see that we call this the residual field, is two terms, and we call this the forward field through the first layer. So this is the input data actually, and this is we can calculate it from our definition. If we use the L2 norm, so we have such term, and it depends on what the activation function you use, and then you get some form of the derivative. Sorry. Okay, now, yeah, so it is saying that if G is this guy, so we'll have G, partial G over partial Z like this. But if you use other activation function, then the form will change accordingly. So then we have the expression of the gradient like this. This guy is our gradient, and here I. What is I represent for? I is means the certain nodes. Sorry, not certain node. I represent yes. I represent a certain node in the first layer, and the summation over I means you should sum all the residuals from different nodes, and K means the certain iteration in the steepest descent method. So it's used to update. So here still should be K plus 1, not K, right? You use previous stage result to update in this stage. Okay, yeah, to make it more clear, you can find each term in this expression. So here, the green one is our input, and the red one can be this guy. So you can see this form G1 minus G. So here, something 1 minus something. So it's the same form. It's just a substitution. Okay. So, is it clear? Do I move too fast, or is that okay? Yes. Yeah, if it's too fast, then just let me know. Okay, now it's more tricky. How about 2 layers? We just work out for 1 layer, so about 2 layers. So 2 layers, as we just discussed, how many layers? It just depends on. We can just derive from the back and to the front. So layer by layer. Now, as we already know how to do the calculate the gradient with 1 layer, then we can do multi-layers. Okay, so here we divide the screen by 2 parts. So the upper half is what we just talked about, the case for 1 layer, and then we use it and do the same thing for 2 layers. So we follow step by step so you can understand more easily. Okay, now we don't use summation first. Let's first only work on one sample. So make the problem easier.